Today I will present about eternal vertex cover of bipartite and co-bipartite graphs, and these are my co-authors. Our problem is a dynamic variant of the vertex cover problem. In this problem, guards are placed on some vertices of a graph, and we have a two-player game. So there are two players, one is attacker, other is defender. So in every move, the attacker attacks an edge, and in response to the attack, the defender moves the guards along the edges in such a manner that at least one guard moves along the attacked edge. So one guard has to move across the attacked edge, and all the other guards can stay on the same vertex or can move to their neighboring vertices. If at any point such a movement is not possible, then attacker wins. And if the defender can defend an infinite sequence of attacks, then the defender wins. The minimum number of guards with which the defender has a winning strategy is called the eternal vertex cover number of the graph G, and it is known as the EVC of G. So I would show this game with the help of an example. So consider this graph. Consider that the vertices which are marked with star are occupied by guards. Now suppose this edge is attacked. Then the guard moves along this edge to defend the attack. Now the edge is repaired. Now, if nobody else moves, then this particular edge, which both endpoints don't have guards, will be attacked in the next move. So somebody has to come on one of these endpoints. So suppose this guard comes on one of the endpoints to protect the edge. Now that edge is not vulnerable, but this edge has become vulnerable. So this guard must come either here or here. But if that guard comes on either of these vertices, then another edge will be vulnerable among these two edges. And if this guard comes here, notice that we have a clique here of size 4 and we need 3 guards to cover this clique. So if this guard comes here, we will have only 2 guards here. So we'll have a edge here which does not have guards on both the endpoints, or we will have a vulnerable edge in this clique. So in the next move, no matter what the defender does, the attacker will find a vulnerable edge, and so the attacker will win. Now I will give some background information about this problem. So we are all familiar with the minimum vertex cover number of a graph. For a graph G, a set S is said to be a vertex cover if for any edge UV in E of G, either U belongs to S or V belongs to S. And the size of smallest vertex cover of the graph is called the minimum vertex cover number of graph G. That is the MVC of G. And in this particular graph, we can see by this example that the MVC of G is 2. And here I would also like to note that the EVC of G always has to be greater than or equal to MVC of G. Otherwise, if we don't have a vertex cover in the first move, then the attacker can attack that edge, and that attacker wins in the first move itself. So connected vertex cover number of a graph. For a graph G, a set S is said to be a connected vertex cover if for any UV in E of G, either U belongs to S or V belongs to S, that is, it must be a vertex cover. And also the additional condition that G of S is connected, that is, the subgraph induced by S is connected. And the size of the smallest connected vertex cover of the graph is called the connected vertex cover number of graph, that is CVC of G. So in this particular example, we had seen that these two vertices form a vertex cover, but the subgraph induced by them will not be connected. So this is not a connected vertex cover. And for connected vertex cover, we need 3 graphs. So CVC of this graph is 3. Now we will state some known results about the EVC number. So basically this problem was introduced by Klostermaier and Meinhardt in 2009. And here they had shown that AVC is between MVC of G and price of MVC of G. And I had just stated the proof of the lower bound. And in this paper, they also gave a characterization of the graphs for which this upper bound is achieved. The characterization for this lower bound is still open. And Babu et al. Has given such a characterization for some particular classes of graphs, which include chordal graphs and internally triangulated planar graphs. Now I will state some algorithmic results about the EVC number. So first is that it is NP hard to decide whether K guards can protect all the edges of the graph. This result was given by Fominator. And in this paper, they had also given the two approximation algorithm for the EVC problem. And this algorithm has running time 2 to the order of root n, where n is the number of vertices and m is the number of edges. And this problem admits a kernel of size 4 to the k times k plus 1 plus 2k. That is, this is an exponential order kernel. And so the question arises that whether this problem admits a polynomial time kernel or not. And here we have resolved this, that it is very unlikely to admit a polynomial kernel. The red-blue dominating set problem. So here we have a bipartite graph and an integer k, and we want to find whether there is a subset of R such that every vertex in B has a neighbor in R, in this particular subset. And the vertices in blue B are called as blue vertices, and the vertices in R are called as the red vertices. And it is known that this problem does not have a polynomial kernel and more generally a polynomial compression unless co-NP is in NP/poly. So this is what a typical instance of red-blue dominating set will look like. And notice that this first 3 vertices forms a dominating set of the blue vertices. So I will pause for a moment to verify that. Now we will state our results for bipartite graphs. So the main result is that there is a polynomial parameter transformation from red-blue dominating set parameterized by number of blue vertices plus k to the eternal vertex cover parameterized by solution size. So this is what a typical instance of red-blue dominating set will look like, and we will reduce it to a typical instance of eternal vertex cover. So now this is how the construction works. So first we keep the original graph as it is, all the vertices and edges as it is. Now we will add one more vertex. We will call it the universal vertex, and we will add edges from this vertex to all the red vertices. Now we add b square plus 3 many dependent vertices for each blue vertex, and we add edges from these vertices to the corresponding blue vertex. And also same for this universal vertex. Note that it is enough to have more than b square plus 3 vertices, but we can have any polynomial number of dependent vertices as long as it is more than b square plus 3 for the proof to work. Now we add another special vertex. We call this as the backup vertex, and we add another edge from the backup vertex to the universal vertex, and we call this edge as the bridge edge. So here the construction is completed. This is what our graph will look like. So here are some observations. The vertex cover number of this graph H is b plus 1. And we can observe that the set of blue vertices plus this universal vertex will form a vertex cover for this graph. And we can verify that we don't get a smaller vertex cover. Any vertex cover of H that has at most L vertices, where L is b plus k plus 2. So any vertex cover which has at most this many vertices must contain set of blue vertices and the universal vertex. This also can be observed easily. Now, I will give the proof of the forward direction. So in forward direction, we need to prove that we have a yes instance of red-blue dominating set, and from that we get a yes instance of eternal vertex cover. But before giving the proof, I will just illustrate the proof idea with the help of an example. And after that, I will give the formal proof. Recall that this G, because we are in a yes instance, it has a RBDS of size K and L is B plus K plus 2. Now, any vertex cover of size B plus K plus 2 must have all the blue vertices and the universal vertex. And also, we maintain the invariant that all the vertices corresponding to the RBDS of G, that is all the K many vertices, must have a guard. So, depending on the position of the remaining guard, notice that we always maintain the invariant that the dominating set vertices will have a guard, as well as the blue vertices and the universal vertex have a guard. So we have fixed the position of B plus K plus 1 guard. And depending on the position of the remaining guard, we have different type of vertex covers. And we had given a proof in which we can defend attacks on all edges in all those types of vertex cover. So I will just be illustrating here this proof with just one example. So notice that this is a dominating set and there are guards, and the extra guard is on the backup vertex. Now, suppose that this edge is attacked. So this guard must come down to protect it. Now the edge has been repaired. But notice that now all these edges are vulnerable. So to protect that, somebody must come to this vertex. And since we have a dominating set at top, then one vertex from the one guard from the dominating set vertex can come down to this vertex. So this guard has come here, and now all these edges are taken care of. Now we are maintaining the invariant that we will always have a dominating set at the top. So to maintain that invariant, the guard on the universal vertex must come up. So this guard is coming up, and now all these edges are vulnerable. So to protect that, the guard on the backup vertex comes to the universal vertex, and now we again have another vertex cover. So this particular attack has been defended, and we can do similar type of things for all the attacks. So now I will be giving the outline for the shorter proof in the forward direction. So from a yes instance of red-blue dominating set, we want to obtain a yes instance of eternal vertex cover. Consider a dominating set of G and let that be V1 up to Vk. And corresponding to the dominating set, let S star be the set of red vertices of H, which correspond to the dominating set of G. Now notice that if G has a red-blue dominating set of size K, then connected vertex cover number of edge is at least B plus K plus 1. And this can also be verified. Now we have this known result from Kostermeyer and Minhart 2009 that EBC of H is always less than equal to CBC of H plus 1. CBC is the connected vertex cover number. And using the previous claim, we have CBC equal to B plus K plus 1. So we get EBC of H less than equal to B plus K plus 2. So we have a yes instance of eternal vertex cover. Now I will give the proof outline for the backward direction. So in backward direction, we have to go from a yes instance of eternal vertex cover to a yes instance of red-blue dominating set. That is, we need to show that any sequence of edge attacks can be defended by deploying at most L, that is B plus K plus 2 many guards. Let S denote the initial placement of guards, that is the set of vertices corresponding to the guards. Now we have two cases. Either it contains the backup vertex or it does not contain the backup vertex. If it contains the backup vertex, in that case, we have shown that the set of red vertices who have a guard or who have a blue neighbor, whose dependent neighbors have a guard, correspond to a dominating set of size k or less. And I will not be giving the proof here, but the proof is given in the paper. And if we don't have the backup vertex in S, then we attack the bridge S, and so one guard is forced to go to the backup vertex from the universal vertex, and then we are forced in case 1. So this was the outline for the backward direction. So now the outline for the proof is complete. Now I will be stating the result for bipartite graphs. So eternal vertex cover problem is unlikely to admit a polynomial compression parameterized by the number of guards, even on bipartite graphs of diameter 6. Notice that the graph which we constructed, it had diameter 6. This same proof also works for eternal connected vertex cover. Both eternal vertex cover and eternal connected vertex cover are NP-hard even on bipartite graphs of diameter 6 because red-blue dominating set is NP-hard. And both of them are unlikely to admit polynomial kernel even on bipartite graphs of diameter 6. Now we will go to the case of co-bipartite graphs. So the main result for this case is that there is a polynomial time, that is a quadratic time algorithm for eternal vertex cover on the class of co-bipartite graphs. Consider a co-bipartite graph with bipartition AB. Here A and B are cliques. A has P vertices, B has Q vertices, P less than equal to Q, and no vertex in B is universal. For any co-bipartite graph which is not a clique, then MVC of G is P plus Q minus 2. This can be easily observed. We know that for a graph with n vertices, in particular this co-bipartite graph with n vertices, if we have just one vertex which does not have a guard, then we are able to defend all the attacks. So we have EBCG between P plus Q minus 2 and P plus Q minus 1. And MVC of G equal to P plus Q minus 2. Notice that the first inequality was because EVC is always greater than equal to MVC. If we use the P space algorithm given by Fomin et al., then we get a polynomial time algorithm for co-bipartite graphs. And if we want to improve the runtime, we can improve it to order n square as follows. We observe that EVC of G is equal to P plus Q minus 2 if and only A and B both contain at least 2 non-cut non-universal vertices. We have given this proof in the paper. And the existence of cut vertices and universal vertices can be checked in order n square time. So we can find out the EBC of any co-bipartite graph in order n square time. So I will just be illustrating one example here. So this is an example of a co-bipartite graph where P plus Q minus 2 guards are sufficient to defend all attacks. And I will be showing the example with the help of one attack. So if this edge is attacked, a guard moves across the edge to take care of the attack. Now the edge is protected. But notice that now this edge has become vulnerable. So somebody must come to take care of this edge. So another guard comes down to take care of this edge. And now this edge is protected. Now this edge has become vulnerable. So a guard moves here to take care of this edge. And now this edge is safe. And now notice that we have a vertex cover again. So we have defended attack on this edge successfully. Now I will be giving some concluding remarks. So we have shown the hardness of eternal vertex cover on bipartite graphs of constant diameter. And under standard complexity theoretic assumption, we have shown that this problem does not admit a polynomial compression. And this same proof works even when we parameterize by the vertex cover number. So it will be interesting to pursue improved FPT and approximation algorithm for these particular classes of graphs. And it is also still not clear whether the eternal vertex cover is in NP even on these particular classes of graphs. These were some of the references which we used. Thank you so much for watching my presentation.